Hi there, this is the first of two videos on kinetic parameters and principles. Now you may well remember that kinetic means moving, so this is all about movement. It's about velocity, it's about acceleration, distance covered and time and so on. And we'll go through these. The first lesson will be basically going back over stuff you did for GCSE, and then the second lesson will be taking it a bit further on, and we'll show you different methods of approaching these problems. So let's get started. So, kinetic parameters and principles. In engineering, lots of things move very, very quickly. They can accelerate very, very quickly, decelerate very, very quickly. Sometimes they accelerate and decelerate very slowly. So what we need to do is to be able to calculate these correctly. And so the aim of this lesson is first of all to go back over what you did for GCSE, the calculations for velocity and acceleration, and then build on that so you're then ready for the second lesson when we look at more complex calculations. So first of all, what's the difference between speed and velocity? Why do we always refer to velocity in these problems? Well, first of all, there is a subtle difference between them. Speed is a scalar quantity, which means it's got a value, but it doesn't necessarily have any direction to it. And other examples of scalar quantities are temperature, energy, and mass, and so on. These don't have any direction at all. They just happen. Temperature can't have a direction, and speed doesn't have a direction. However, velocity has speed and direction, and that's what makes it a vector quantity, which means on a diagram we can draw velocity as an arrow showing its direction and its strength. And other examples of vector quantities are voltage and also force as well. And in most direct engineering situations, the velocity or the direction you're going is as important as the speed as well. So velocity calculations, from GCSE, you should remember that velocity is simply how far you travel in a given time. So the velocity equation, hopefully you can remember this, is distance over time. And we typically measure things like, for example, miles per hour, how many miles you travel in an hour. In engineering calculations, we refer to meters per second, how many meters you travel per second. So, for example, if you travel 150 meters in 3 seconds, you can very easily calculate your velocity. 150 is the distance traveled, divided by 3 seconds, gives you 50 meters per second. That's your velocity. And similarly, distance travelled, you can rearrange the equation very easily to work out how far you've travelled if you've been travelling at a particular velocity for a certain length of time. And an example here is having rearranged the equation, distance equals velocity times time. So for a vehicle travelling at 35 metres per second, therefore every second it travels 35 metres for 2 minutes, you can calculate the distance it will travel in 2 minutes, simply 35 metres per second for 120 seconds, the same as 2 minutes, gives you 4,200 metres or 4.2 kilometres. So here's the first practice question. So pause the video now and have a go at this yourself, and then restart the video when you've finished and we'll go through it and see if you've got the right answer. Okay, the answer you should have got for the first question is 56.25 metres per second, and the answer for the second part of the question is 1750 metres, 1750 metres. If you got that, well done. Skip on to the next section. Otherwise, let's go through it. Okay, so for practice question 1, calculate the velocity of a railway locomotive that covers 4.5 kilometres in 1 minute 20 seconds. So we know that velocity equals distance over time So in this case, the distance 4.5 kilometres is 4,500 metres. Just multiply the 4.5 times 1,000, and the time is 1 minute 20 seconds, so that's 80 seconds. So the answer to that is 56.25 metres per second. Okay, second one. A bullet leaves a gun at 700 metres per second and travels for 2.5 seconds before hitting the ground. What distance does it cover? So we can use this equation here and rearrange it so distance equals velocity times time. And this to say 700 times 2.5 equals 1750 metres, or 1.75 kilometres. Okay, so what about acceleration? That's what we're often more interested in, really, than how fast you're going. How quickly can you accelerate? Now, acceleration is the change in velocity divided by the time it took to make that change. And the equation there, again from GCSE, acceleration is the change in velocity divided by time. So if we look at this, a vehicle accelerates from rest to 5 metres per second in just 2 seconds. You need to calculate the acceleration. Now in this particular example, from rest means 0, so the change in velocity is simply 5 divided by 2 because it starts from rest, and that gives you an acceleration of 2.5 metres per second squared. That means every second you're going 2.5 metres per second faster than you were the previous second. So that's acceleration. Now deceleration is negative acceleration. And an example here, car braking, quite obviously. A vehicle brakes from a velocity of 30 metres per second to a standstill in a time of 6 seconds. Calculate the deceleration. So simply you're getting the equation here. The deceleration is the change in velocity, and in this case you're starting at 30, going down to 0, so the change is 30, and it takes place over 6 seconds. Your deceleration is 30 divided by 6, which gives you 5 metres per second squared deceleration. So it's quite straightforward to work out acceleration and deceleration in these situations. So let's look a bit more at acceleration. So normally with acceleration problems, you've got two velocities: the starting velocity at the beginning of the problem and the final velocity at the end of the problem. And usually for equation purposes, we use the symbol U for the velocity at the start of the problem and V for the velocity at the end of the problem. And we'll see some more examples excuse me, when we do this. So for deceleration problems, the U at the velocity at the start of the problem will be higher than the velocity at the end of the problem because you're actually slowing down rather than accelerating. So let's do a sample calculation. So here we have a motorbike accelerates from a velocity of 15 metres per second to 35 metres per second in a time of 5 seconds. So you need to work out what the acceleration is. So the equation we're going to work on is the change in velocity, which is the final velocity minus the initial velocity, v minus u, divided by t, and that then gives us 35 minus 15 divided by 5, which gives you 4 metres per second squared is the acceleration. And again, this is how you need to lay it out when you actually go about doing an exam question, or any engineering question for that matter, so it's very clear what you're actually doing. So what happens if the object is already moving? Now this particular equation here can be created from the equation on the previous slide by rearranging it. And this one here shows us that the final velocity is the initial velocity plus the amount of acceleration, the amount of time it takes for that acceleration. Now this is an equation you're actually given on the formula sheet. You don't need to remember this. And if we actually go ahead and use it, here we have a car travelling at 25 meters per second, accelerates for 4 seconds at 2.5 meters per second squared. What is its final velocity? All you need to do is to put the numbers into the equation. So it starts off at 25 plus 2.5 times 4 gives you 35 meters per second squared. It's quite straightforward. So here's another practice question for you. A car moving at 6 meters per second accelerates for 6 meters per second squared for 30 seconds. What is its final velocity? So again, pause the video, have a go at this, and then restart the video to find out the correct answer. Okay, the answer you should have got is 186 meters per second. If you got that, well done, go on to the next section. If not, let's go through it. Okay, for practice questions 2, a car moving at 6 meters per second accelerates at 6 meters per second squared for 30 seconds. What is its final velocity? Now, for this one, we're going to use the v, final velocity equals u plus at. So simply put the numbers in. U is the initial velocity, so that's 6, plus 6 meters per second squared is the acceleration, times 30 equals 186 meters per second. Multiplying that through together. So, what about the distance travelled when accelerating? If we just take it back a step and we review how you actually calculate the distance when you're travelling at a constant velocity, we get what we've got on the screen here. So, for example, if you're travelling at a constant velocity, the distance travelled, as we know from the previous equation, is the velocity times the time. And if you put it onto a velocity time graph, which we've got over here, if we've got the velocity up the side on the y-axis, the time on the x-axis, and for example, if you're travelling at, say, 5 meters per second for 10 seconds, for example, the distance travelled will be 50 meters. And that is effectively the area, was the same as the area under this velocity time graph. So the area under a velocity time graph is the distance you've actually travelled. And this then gives us this equation here. Same kind of thing. We've got a velocity time graph, velocity going up here, time going along the bottom. And in this one here, you may remember from GCSE, you've got your initial velocity here, your final velocity here as you accelerate. The area under an area like this is simply this equation here, which is half of u plus v. So we've got u, the starting velocity, v, the final velocity. You add the two up, divide them by 2, and effectively this gives you this height here. And then you multiply that, the average velocity whilst you're accelerating, by time, and that gives you the distance travelled. So if we look at this, for example, with the motorbike problem we had from the previous question, we can simply put the numbers in, and it's half times 15 plus 35, the initial velocity plus the final velocity. That gives you the average velocity during the 5 seconds, multiplied by 5, gives you a distance of 125 meters travelled. So it's quite straightforward to actually, if you think about it as a graph, to actually work these things out. Now the good news is that this equation here is actually one that's you get actually in the exam on the formula sheet. So I've got a summary now of the equations you might actually want to use. And here they are. The velocity equals distance over time, and acceleration is change in velocity over time. You will have to remember these, but hopefully you can remember them from GCSE anyway. They are fairly self-explanatory. But these two here, with u and v on them, the v equals u plus at, and the distance travelled, which is a half u plus v times t. These two in the green are given to you on the formula sheet. You don't have to remember them, but as always, you do need to know how to use them. So let's look at another practice question here. Here it is. And so an airliner starts its takeoff run at 5 meters per second and leaves the runway, becomes airborne after 15 seconds. What you've got to do is to calculate the average acceleration and also work out what the minimum length of the runway must be for that to happen. Have a go at this, and then I'll give you the answer when you restart the video, and I can go through it if you're not sure. Off you go. Okay, the answer you should have got for the acceleration is 7.67 meters per second squared, and the answer for the length of the runway, minimum length, is 975 meters. If you got that, well done. If you're not so sure, that's okay. We'll go through it. Okay, for practice questions 3, an airliner starts its takeoff run at 5 meters per second and leaves the runway at 120 meters per second. This takes 15 seconds. Calculate the acceleration. So acceleration is change in velocity over time. So I'll put that in here. And the change in velocity is the final velocity minus the start velocity minus u over t. In this case, 120 minus 5 divided by 15, and that comes to 7.67 meters per second squared. So that's fairly straightforward, just putting the numbers into the basic acceleration equation. The second part, what must be the minimum length of the runway? So for this, we can use this equation here, where distance so put that into there, put the numbers into here, half, and then a u is 120 plus 5 multiplied by t, which is 15, and when that's all multiplied through, that comes to 975 meters. Now the nice thing about these questions is both of these formulas are on the formula sheet, so you don't have to remember them. Probably you will do if you do lots of practice, but that's what you need to do for those questions there. So here we are at the end of the lesson. These are some assumptions that we've made from this particular lesson. First of all, we always assume the acceleration is linear. It's a constant acceleration. In reality, this isn't usually the case. And I've got an example here on the right-hand side of the acceleration of a sports car, starting off at 0 from the traffic lights or something like that, right up to its maximum speed. And you can see here you've got these little dents, little kinks in the acceleration. That's where you change gear. And you can see from this is a pretty fast car. 0 to 60, the scale here is kilometers per hour. And then another scale's kind of superimposed on it, miles per hour. And you can see 0 to 60 in probably around about 6 seconds. Top speed, getting on for 140 miles an hour. It's a pretty quick car. But although you can see the acceleration does drop off as it gets faster, each individual bit, for example, if you look at the acceleration in third gear, it's almost linear. Certainly down here, the acceleration is almost linear. And again, if you look up here, just a little bit here, the acceleration is almost linear. Now, you don't have to worry too much about the drop-off of acceleration. For your purposes, we will always calculate assuming constant acceleration. Just to bear that in mind, really, this is an assumption we make on these calculations. Now, once you've finished the video, have a go at the practice questions. There are some practice questions on this. Have a go at those. They do have the answers on them, so you can check your work and so on. And then you're ready then to go on to the second of these lessons in the series. See you later.